Okay, so now we're going to have some more fun with Maclaurin series. And if you recall, in the last video, we looked at what a Maclaurin series meant, and it was just a power series that you associate with a function. There's actually a formula for it. You build up, we said, okay, if they converge to each other, then a function is equal to its Maclaurin series, which is the sum of is equal to 0 f to the nth derivative evaluated at 0 divided by n factorial times x to the n. And randomly, if you like, that's f of 0 plus f prime 0 over 1 factorial x plus double prime of 0 over 2 factorial x squared, blah, 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 blah. That's a Maclaurin series. And some nice ones, this is just a screenshot from your textbook, are these. We haven't really looked at arctan yet, so let's, you can forget about that for now. But we used the formula, and we figured out that for these particular 4 functions, these are their Maclaurin series. These are all in your formula booklet as well. But what if we wanted to take the Maclaurin series of another function? Well, of course, you can always do that, because you can just use the formula. That will always work, as long as the function is differentiable. But let's there's some shortcuts. We don't have to use the long way and do it the formula every time. So let's do one example. For instance, what if we wanted to calculate the Maclaurin series for the cosine of 2x cubed? Okay, well, like I said, we could always use, okay, let's use this formula. Yeah, 0 over factorial x to the n. Okay, so let's see, we need some derivatives. First derivative is, oh goodness, let's see, negative sine 2x cubed. Now it's chain rule. The derivative of the inside is 6x squared. That's not nice. And then I do another derivative. I have to use the product rule. I don't want to do this. I don't want to do it. I could. Take me forever. Maybe there's a better way. Well, let's see. We know that the cosine of x is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and this converges for all x. So this series is literally equal to cosine of x for any x. But okay, so what if we plugged in for x 2x cubed? Wow, this looks nice. Okay, look at that. Now we're getting somewhere. So we can do that. Now, let's see. We can even 1 minus 2 squared is 4 to the 6 over 2 factorial. 2 to the 4 is 16. Divided by 4 is 4. X to the 12 over 3 factorial. And you could keep going if you liked. And you know what? Let's simplify this a little. 1 minus x, that's right, 2x to the 6 plus 4 divided by 3 factorial as, well, there's a 2 in there, so it's 2x to the 12 over 3, blah, blah, blah. And you could get as many terms as you want. It's very easy if I wanted to add another term. Up here, this would be minus 2x cubed to the 6th over 6 factorial. And let's keep going. This would be, let's see, 2 to the 6 is 64. 64 is not divisible by 6. There's 64. 6 doesn't go into that. Simplify it, I think you get minus 4 over 45 x to the 18 So this would be our infinite series for cosine of 2x cubed. So just from already knowing cosine, we can do a composite function. Now, if we have a composite function where the outer function is a series we know, we can just plug into that composite function series to get a new series. Let's do one more. So let's do the Maclaurin series for sine of x and e to the x. Let's use our knowledge of those to make a composite function of e to the sine x. Okay, so let's recall up to the x to the fourth term. They don't mean to go forever. Let's see, e to the x, we remember that's this factorial, blah, 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 blah. And let's see, sine of x, this is the odd powers of x, is how you should remember it. Okay, and we need to combine these. And how are we going to do that? This one's actually a little tricky because we're using exponentiation, but let's see, e to the sine of x, that's e, and that's, okay, this is like x minus x cubed over 3 factorial plus x to the 5. We know we're not going to have to go up to x to the 5, so let's just cut it off here, and we know that because we're only asked to go up to the x to the fourth term. And okay, by our exponent laws, this is actually e to the x times e to the negative x cubed over 3 factorial, blah, blah, blah. And we can expand each of these. Okay, e to the x, this is just 1 plus x squared over 2 factorial plus, I'm missing one, sorry, 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. And of course, you could simplify all these factorials if you wanted to. Okay, so this, now the right, so this e to the x, that's all of this. And in green, let's do this. So this is actually also a composite function. This is the series I just wrote out, but instead of writing x, I'm going to substitute negative x cubed over 3 factorial. So what does that end up looking at? Well, 1 doesn't change. If I plug, instead of an x, I now have a negative x cubed over 3 factorial. And I know I can't use a higher term because that's going to give me something more than x to the 4 term. Because if I was to plug in another term, I would take negative x cubed over 3 factorial and square it. I would get x to the 6th over 3 factorial squared divided by 3 factorial, which I don't need x to the 6 terms. And we can imagine now using the distributive property. So if I took this 1 and multiplied it through, for instance, I would get 1, let's go back to red, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus a bunch of stuff. And then I can also imagine doing the same. We have like an infinity of infinity terms here because we can, for each of the infinite terms on the left, we can distribute across one of the terms on the right. This guy can also distribute around. So this would be plus negative x cubed over 3 factorial and minus x to the 4 over 4 factorial and minus x to the 5. And I don't know where I got 3 factorial from. That should be 3 factorial again. This one should be 3 factorial 2 factorial. And then this should be x to the, well, actually I know I don't need any x to the 6 terms, so I'm just going to stop there. So it's very nice that they told me to stop at x to the 4. There aren't actually that many x to the 4 terms. Sorry, I'm just trying to give myself some more space here. Okay, so this is going to be, let's see, 1. There's only one x term. There's only one x squared term. Ooh, look, these cancel out. That is pretty nice. And there's only, let's see, so I need all the x to the 4 terms, so I should have went one further. My original would be x to the 4 over, that comes from this. So then, look, that cancels. That almost cancels. I have x to the 4 over 4 factorial here, and I have minus x to the 4 over 3 factorial. And then all the other terms I have are not going to be x to the 4 terms. Right? They'll all have power 5 or higher. And let's clean this up. So this is 1 plus x plus squared over 2 factorial is 2. Now this is x to the 4 factorial. 4 times 3 is 12 times 2 is 24. Minus x to the 4. 3 times 2 is 6. Okay, let's finish this off. This is 1 plus. Okay, so this is 1 over 24 x to the 4 minus 4 over 24 x to the 4, so minus 3 x to the 4 over 24, 1 plus x squared over 2 minus x to the 4 over 8. And we have higher degree terms that we are not asked to figure out. So this weird series that we got from e to the sine x is actually equal to 1 plus x squared over 2 minus x to the 4 over a plus some higher degree terms. So that's a pretty tricky one. The first one is pretty straightforward, I would say, just plugging in 2x cubed to cos x. This one's pretty tricky. Try the homework questions in the book. Here they are. And give them a good try. And then when I get back, we will, of course, take this up and we'll go into some finer points about Maclaurin series and then examine their big brother, the Taylor series.